this computer? Great. So we're doing conditional probability. So let's start with a standard deck of cards. If you have a standard deck of cards and a standard deck of cards, how many cards do we have? 52. And what's the probability I would draw a queen? How many queens do you have in a standard deck of cards? 4. So we would say 4 out of 52, right? 4 divided by 52. Which reduces to 1 out of 13. Okay, great. Now, what if I pick a card and it's a king? So let's say I pick a card and it's a king. And I keep it. Right? And I keep it in my hand. How many cards would I have left in that stack? 51. Agreed? We would have 51 cards left. I'm gonna right now, I'm gonna pretend to do it so I don't get hollered at because there's a lot of people missing, and then I'll do it formally. There's a lot of people missing. Thank you for reminding me. So I have 51 cards left. Now, if I ask you, what's the probability of getting a queen given I just drew that king, what would you say it would be? 4 out of 51. And this is what a conditional probability is. This is read as the probability of queen given king. In this case, because we kept the card, the king, we kept it. We altered the probability of queen because under normal circumstances, the probability of queen is just 4 out of 52. But because we had already had the event king happen and we kept the card in our hand, that means when we keep it, we say it's without replacement. That's what we mean. In effect, the event king altered the probability of queen. And that's what a conditional probability is. Now, I could change this slightly. I could do the same thing I just did, right? Go ahead and write on the other side. So what if instead I picked a card and it's king, but instead of keeping it, and I put it back? So in this case, I picked the card and it's king, but then I put it back. In this case, we will say this is with replacement. Then I ask you, what is the probability I get a queen given I just drew the king? What would it be now? I put the king back in. 4 out of? In this case, we still have a conditional probability, but in the case on the left, events king and queen were dependent. In this case, events king and queen were independent. Why? Because the probability didn't change because the other event happened. Is that pretty clear? Now notice something. Notice that the probability of queen in this case is equal to the probability of queen given king. In other words, king didn't have an effect on the probability of the second event. It did not. In this case, the probability of queen versus the probability of queen given king, they're different. Therefore, the events are dependent. So we can make a statement right now. I'll write it here. If events are independent, and I should rewrite if events A or B. Events are independent. Missing a bunch of letters. Independent. Probability of A given B must equal to the probability of A. Or probability of B given A is equal to probability of B. Else, let me not do that. If events are independent, probability of A given B must equal probability of A, probability of B given A equals probability of B. Now, if that's not the case, then they are dependent. So to show that something is dependent, you show that its probability and the conditional are not equal to each other, and you're good. Now, there will be homework on this. And again, the ideal here is that right now, you're paying attention to this, and you're trying to keep your mind from meandering to wherever it's going to go to, and you're staying focused. And then you go home, you have that time, you separate to work on this assignment, and you come next class and talk to me about this. That's what we want ideally. Okay. So then I can write, after explaining that, else the events would be dependent. And I'm going to scroll that up so everybody can see that. I'm going to give you another example of independent events. So, example. What's the probability of getting tails when you flip a coin? So we say this is half, right? When we roll a die, what's the probability of rolling a 6? No, 6. Now let's consider the following event. What's the probability of rolling a 6 given I just got tails? So I tossed the coin, got tails. Great. Now I'm gonna roll a die. What's the probability of getting a 6 when I roll that die given I just got a tails? Do you see that the probability of 6 equals the probability of 6 given tails? That means the events 6 and tails are independent of each other because the flipping of the coin had no effect on the rolling of the die. That's what this means. That's what this means. Since tail didn't have an effect on 6, then it's independent. And we show it that way. Make sense? Trying to be as thorough as possible. Okay. Let me give you another example. And we just did this one. So the probability of queen is 4 out of 52, correct? Now, imagine I'm picking two cards. My first card was a king. I keep it. Usually what they're going to say is they're going to say without replacement. That's the key word. So then what would be the probability of getting a queen given I just got the king? And we said it was what? 4 out of 51. So therefore, since the probability of queen given king does not equal the probability of queen, we say the events are what? Are they independent or dependent? Dependent. Dependent. How do you make this independent? You do what? You change one thing. You change if you put the card back in, which is we mean with replacement, then what happens now? The events become independent. When you have that, you'll have that the probability of queen given king is 4 out of 52. So therefore, in that case, you have that the probability of queen given king equals the probability of queen. Good? Make sense? Okay. So now I have to introduce to you the multiplication rule. The multiplication. Missing letters. And let me not be so sloppy and separate things with a ruler and, you know. Does it look like it's gonna rain today? Or is it just cloudy? Should I walk around for lunch or should I meditate? Okay, I agree with you. I'm going to meditate. Huh? The thing is, you're supposed to walking won't allow you to meditate, I think. I'm not sure about that. I know you could be lost in thought while you're running, or sometimes I don't know. Okay, so let's look at the multiplication rule. The multiplication rule goes something like this. The probability of an event A and B happening, one after the other, equals the probability of A times the probability of B given A, or sometimes you could say as the probability of B times the probability of A given B. If the events are independent, then the probability of A and B must equal the probability of A times the probability of B. Now, just to mention, the probability of A and B and C and so on, as long as they're independent, you can just multiply them straight through. Okay? Still know that your teachers are using the tablets? Why? Are any of your teachers fasting? Yes. The last one?
Yeah.
Yeah, so which part are you here or there? Okay, here's what I'm gonna say right now, and it'll become clear to you when we do the question, which we're gonna do. Write it down. You'll see right now when we do the example, hopefully it should click in. Some people can click on it. Like it took me forever to really understand this. Because the way I would do it is the teacher gives me this and I would just follow the rule, which you'll see. I'm gonna do it right now with a rule, but then I'm gonna try to explain the rule to you. And you're gonna hopefully understand it. So I am going to try and explain it to you because I want to explain it to you. Now, the question is, do I want you to learn it? The answer is yes, but how much am I willing to, to, to go over something? The answer is we have limits because sometimes we feel that some kids actually want to learn versus some that don't. So the kid that wants to learn, you want to help them as much as you can. And the kids who don't, you want to ignore them, right? Does that make sense at all? Like the kid who's not doing anything, hasn't done anything from the beginning of the year, cheats and stuff like that. You don't want to but now you want to know, you know? And so I know it's wrong, but does that make sense? Okay. Anyways, but I will do my very best to explain it to you. In fact, I'm gonna just go straight to you when I'm explaining it, which I'm gonna do right now. So let's talk about this. And here's the example. I'm gonna do it in red. But I need you to think, what's the probability of me getting a king and a queen and a deck of cards?
8 out of 52.
We're doing two things. We're going to pick two cards. What's the probability of me getting a king and a queen? If you follow this rule, and so let me rewrite this and give us some space. So here's how I would do this, right? Like usually when the teacher taught this lesson, I would just write the rule up top like this. And I would write that's probability of A times the probability of B given A. And then you would write, okay, Mr. Coso, you're asking for a probability of king and queen. And you write, okay, that's going to be the probability of king because king is taking the place of A. And you write Q given A. Right? Now, I have to tell you right now that this is without replacement because if I don't say that, it changes the probability. That means you pick the first card, you keep it. Pick the second card, keep it. What's the probability you're actually going to get king and queen? Well, let's see. What's the probability of getting king on my first draw? And as we done, what's the probability of queen given, oops, king? 4 out of 51. Do you know why we're getting 4 out of 51? Yes. And so, yes. So now this is 16 out of, wait, I messed up. Out of 52 times 51. You got to multiply. Yep. Now I want, before I continue, I want to tell you right now that that rule is just the multiplication rule, the counting rule. It's a fancy way of doing counting. Look, think about it. I could pick a king of hearts and a queen of hearts, or a king of hearts and a queen of diamonds, or a king of hearts and a queen of spades, or a king of hearts and a queen of clubs. Or maybe it could have been a king of diamonds and a queen of hearts, queen of diamonds, queen of spades, queen of clubs. Or maybe it could have been a king of spades, queen of hearts, queen of diamonds, queen of spades, queen of clubs. Or maybe it could have been a king of clubs, or queen of diamonds, queen of spades, queen of hearts, queen of whatever. I missed right there. Spades or clubs. There were 16 ways I could have picked a king and a queen. That's what 4 times 4 does for you. 4 times 4 tells you there are 16 ways to pick the king and the queen. Now, what the bottom tells you is how many ways I could pick any card the first time. I could have picked 52 different cards on my first draw. And I could have picked 51 cards on a second draw. In other words, there were 2,652 ways I could have picked 2 cards. But there were only 16 ways I could have picked the king and the queen. And that's what the multiplication rule is. It's a fancy way of me doing that. It's telling you, hey, how many ways can you pick what you want? This way and this way. How many ways can you pick everything? This way times this way. Divide them. That's your multiplication rule. Do you understand that? That's what it's doing. When you multiply this, that's what it's doing. Yeah, that's all it's doing. All it's doing is telling you, hey, apply this rule. Probability king times the probability king, queen given king. And the numerator is taking care of the ways I want. The denominator is taking away the total amount of ways. Okay, so let's do it with replacement. So we're going to do this. So let's say with replacement. So we're going to put the cards back, right? With replacement. So we're going to do this probability of king and queen. The rule still applies. Probability of king times the probability of queen given king. What's the probability of king on the first draw? 4 out of 52. King did happen. Did we put the king back in the stack? Yes, we did. What's the probability of queen now? 4 out of, which is okay. So it's just 16 divided by 52 times 52. Nothing happened because these were dependent events. And as we said in the rule says that if the events are independent, we just multiply the probability of A times the probability of B. Nothing changed. How many ways can I pick king? 4 ways. How many ways can I pick a queen? 4 ways. How many ways can I pick the first card? 52 ways. I put the first card back in. How many ways can I pick the second card? 52 ways. So there's 2,704 ways I can pick the cards. There's 16 that will get king and queen. Make sense? Now, obviously, that takes care of the main rule. Oh, they're giving away free games. Huh. You know what game I started playing over the break? I played Halo Infinite. I thought so far I played it a decent amount. I thought they did a great job with Halo Infinite. There's one I played back like maybe 10 years ago or 7 years ago, something like that. I thought it was okay, but this one's really good. All right. How to stop being shy. Huh. It just came up there. How to stop being shy. Okay, so let me go ahead and look at another example I'm going to be giving to you. Make sure I give you all the proper examples. Okay. So let's continue discussing independent probability. And then I want to go ahead and take a look at a table. And then I want to go and take a look at a situation where we have, here we go, something different. Okay, so what about, I'll give you this situation. What's the probability when I toss a coin? When I toss a coin, I get tails. And when I roll a die, I get a 3. Okay, so the rule will say that there's going to be probability of tails, right? Times the probability of 3 given I just flipped tails, right? What's the probability of tails? What's the probability of 3 given I just rolled, since I flipped the tails? So 1 out of 6. The events are independent, right? What's this going to come out to? 1 out of 12. You see it? How many ways could I flip get tails when I flip a coin? One way. How many ways can I get a 3 when I roll a dice? 1. So that takes care of 1 times 1. How many results can I get when I flip a coin? 2. How many ways can I get results on a die? 6 ways. 2 times 6 takes care of that. This is just counting rule. This is just counting rule. Okay. Yes. Well, in this case, this is so important because the probability of tails and 3. See, you could have gotten tails in 1, tails in 2, tails in 3, tails in 4, tails in 5, tails in 6, or heads in 1, heads in 2, heads in 3, heads in 4, heads in 5, heads in 6. There are 12 possible results that were possible, and only one of them met this criteria. And you didn't have to draw it all out. You see it? Go ahead. Oh, I see what you mean. Could you carry out that experiment if you wanted to? Hey, could you flip a coin and roll a die? And write down each time what were the results? Yes. No, and you can put it together. Why not? The whole point is, don't look at it. I see what you're saying, but same thing with the cards. Could we keep the cards in hand? Could we put it back in? If we put it back in, then why worry about, no. Do you agree that if we have 52 cards, you could go, okay, pick a card. Good. What's the probability it was an ace? Oh, 4 out of 52. Sorry. Yeah, 4 out of 52. Oh, put it back in. Do it again. What card do you get? Oh, I got the 2. Okay. Do it again. And each of them has a probability, but I can ask, what's the probability if you draw it 3 times with replacement that you get ace, ace, and ace? Maybe that's something I'm interested in. That's very different than just restarting and repeating. Hey, what's the probability reset? Yes, the probability is reset at the same time. That's with one event, but maybe I want to consider 2 or 3 events in a row, which is a completely different story. Does that make sense? Okay, there. Hey, am I trying? Does it feel like I'm trying? Why? Why? Yeah, but that's not the easy solution because there's a lot of teachers and there's a lot of students. Do you agree that some students care more than others? And do you agree that some teachers care more than others? And do we agree that the caring is not consistent and may meander from day to day? Some days you care more, some days you care less. So what is the ideal? To strive the best we can every day. Yay. All right, let's continue. All right, so let's try some more. Okay, so here we go. Let's just say that we have people who got A's in this class and people who did not get A's. And we subdivide them into 2 groups of people. into band nerds and into not band nerds, just to see if there is a correlation between being a band nerd and getting an A and not. And what we noticed is in the class, we had 12 band nerds and 13 non-band nerds for a total of 25 people. Right? And we also noticed there were 5 A's and there were 20 not A's. Okay, this is what happened. Right? There's nothing we can do about it. It is what it is. So now I'm going to tell you that there were 3 band nerds who had A's. You see that? That's quite a bit. Are band nerds that smart? How many band nerds do we have in class? No, like in reality. How many band nerds do we have here? No band nerds? Okay. Well, what do I count as a band nerd? Do you play the trigger trombone? You know, like that. No. Oh man, this is gonna come on the recording. Okay, so now let's. By the way, well, I wanna teach this way, but we'll finish it. Okay, if there's 3 band nerds with A's, how many are not band nerds with A's? And then can you figure out this one here? How much does that have to be? 9. 9 plus 3 is 12, right? And then this one is what? You see it? 11, because 11 plus 2 is 13, but 9 plus 11 is 20. 3 plus 2 is 5. You saw how I filled out everything? Okay, so we're going to begin. I'm going to do this in rainbow color. What's the probability of having an A in this class? How many people got A's? 5 out of 25, right? What's the probability of not A? Okay, yes. And do you notice if you add probability of A plus probability of not A, you get 1, 25 out of 25? Okay. So what's the probability of being a band nerd? 12 out of 25. What's the probability of not being a band nerd? Correct. Now, what's the probability of getting an A and being a band nerd? Yes. What is the probability of getting an A and not being a band nerd? 2 out of 25. You see how that's working? You see how that's working? So now what's the probability of not A and being a band nerd? 9 out of 25. And what's the probability of not getting an A and not being a band nerd? 7 out of 25. So far, so good. Pretty straightforward, right? Now, I'm changing what I'm going to say. So let me pick a different rainbow. What is the probability of getting an A given that you are a band nerd? Now, notice what I'm saying. I'm saying, hey, those of you who are band nerds, line up. How many of you have A's? And what you would say what? 3 out of how many? You see that? That is a conditional probability. The probability of getting an A, given that you are a band nerd, is 3 out of 12, because we're reducing what we're talking about, not from the total people, but only those people who are band nerds. Make sense? So now I can ask the question, what's the probability of not an A given that you are a band nerd? And you would say 9 out of 12. And the probability of getting an A, given you're not a band nerd, is 2 out of 13. And the probability of not A, given you are not a band nerd, is 11 out of 13. Have space there. And what's the probability of being a band nerd given you have an A? 3 out of what? 5. The probability of not band nerd given A, not band nerd given A, is 2 out of 5. And what's the probability of band nerd given not A? 9 out of 20. And what's the probability of not band nerd given not A? Well, that's 11 out of. Yeah, well, the probability of band nerd given not A.
Yeah, that's what I'm saying. So basically, it would be that category, but it's the category that has numbers.
Yeah, well, in this case, band nerd given not A's. Yeah, is this on? How many people don't have an A? 20. How many of those are band nerds? 9. Yeah, exactly. That's exactly how you look at this. Now, if I asked you the following question from this here, are events getting an A and band nerd independent? Are they or are they not? Well, let's see. The rule says 2 events are independent if the probability of the event equals the probability of the conditional. So let's go ahead and look at it. Is the probability of A equal to the probability of A given band nerd? The probability of A by itself is 5 out of. Yes. 5 out of 25. And what's the probability of A given band nerd? Three out of 12. Are they the same? Therefore, band nerd had an effect on A. Therefore, these are dependent. In order for 2 events to be independent, the probability of the event and the probability of the event plus a conditional have to be the same. When I flip a coin and I roll the die, it didn't matter. The flip of the coin is always going to be half and half and half. You see? But in this case, there's a change. Therefore, we can see it's dependent. Now, I want you to see that the probability of A and band nerd indeed is the probability of A times the probability of band nerd given A. Well, what's the probability of band nerd of A? Sorry, it's 5 out of 25. What's the probability of band nerd given A? Oh, it's 3 out of 5. Well, we wrote here that the probability of A and band nerd is 3 out of 25. Is that the case? Yes, it is. See, when we started this question, we already had said that the probability of A and banner was 3 out of 25 by visual inspection. Oh, it's 3 out of 25. But when we apply the rule now, the probability of A and B and a banner equals the probability of A times the probability of banner given A. Well, the probability of A is 5 out of 25. The probability of banner, yes.
Well, for the first part, where you have the 5 over 25, not equal to 5 over 12,
3 over 12.
that's a 3.
Sorry about that. That's a 3. That's a 3. Let me fix it here. So, do you see how this came out? Like magic. We were able to do it via inspection, and we're able also to do it using the rule. There's more to this that I can just go down the rabbit hole, but that's not, I don't want to go ahead and do that. None of your teachers are doing this? 2007, 2006, and I started seeing him, so I thought it was reasonable. I like it. All right, let's continue. He knows his stuff. All right, so I should go into one more group of explanations because that took care of this part here, and now we are at the final part. There's one more part, and then we'll be done. Be careful. Okay, so imagine we can magically know or somehow empirically know the probabilities of a successful knee surgery, and we agree that what a successful knee surgery is all about. Objectively. And we say that the probability we're going to have a successful knee surgery is 0.85. Okay, let's say that's the case. Now, could you please tell me if the probability for successful knee surgery is 0.85, could you tell me what the probability of, I'll use the F, of failed knee surgery would be? Yes, it's on fire, it's recording, it's what's the probability of a failed on any given trial of failed knee surgery? What's left over? What's the sum of all the probabilities have to be? So this has to be 0.15. Does that make sense? Okay. So on one operation, what's the probability I will get a good surgery? 85. Now, what happens when I want to do 2 surgeries? The probability of a successful and successful knee surgery. What would it be now? Now, 0.85 times 0.85 because it's 2 surgeries, right? And they're independent of each other. So the rule says just multiply them. But I want you to think of this as a card question. Think of it like this way. Think of it, I have 100 cards. 85 cards are S's. 15 cards are F. What's the probability I draw the first card S, I put it back in a stack, and draw the second card S, and that's it. That's what this is. Does that make sense? If I have 85 S's out of 100 cards, isn't that 85% chance of success? You see that? So what if I played this card game, this same card game we've been playing with the 52 cards, but I have 85 cards that are S's, 15 cards that are failures, that are F's, and I ask you, hey, what's the probability of success and success? With replacement, because each of the events, the first surgery has nothing to do with second surgery. So we pick the first card, OS, put it back in. What's the second? OF, right? The probability of S and S would just be 85 out of 100 times 85 out of 100. And if I ask the probability of S and S and S, it will just be what? 0.85 times 0.85 times 0.85. Does that make sense? Now, obviously, they can't leave it at that. See, that's the first tier of things that could happen. You could have a successful knee surgery or a failed knee surgery. If I try again, I could either have two successes, a success and a failure and a success, and a failure and a failure. This is no different than the question that happens of like male and female offsprings, right? By the time we go to the third one, S, F, S, F, S, F, S, F. Now, I might want to ask a question. What's the probability of at least one success? And what happens is this meets the criteria. That's at least one success. This meets one criteria. That meets one success. And it looks weird, so let me remove that. This meets the criteria. 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 There's only one that doesn't have at least one success, which is fail, fail, fail. So at least one success, you would have to do success, success, success. That's 0.85 to the third. Then you have to do success, success, failure. That's 0.85 to the second times 0.15, right? Then you have to do the next one. You have to do 7 other ones. But something you have to remember, if you did, this is 0.85 to the third, this is 0.85 to the second times 0.15. And you have to do all these. And this last one is 0.15 to the third. If you add all these up, guess what you get when you add up all the probabilities? You get 1. So if you just took 1 minus the probability of no successes, you would get the probability of at least 1 success. 1 minus 0.15 to the third would be your answer. So what I'm going to be doing is I'm going to be assigning the homework. And I'm going to be posting this video. And hopefully if you do the homework and you have questions for me, I can answer it next class. And we can try and get ready for a quiz that we can take. And hopefully those of you who want to do well in the class and who want to have a successful year, new year, whatever that might mean to you, whether you're still cynical about New Year's resolutions or not, we'll be able to advance from